Pleasure to introduce. Oh, okay, sorry. It's again my pleasure to introduce Dennis Kriventsov from Rutgers University, who's going to speak about stationary solutions to the Bernoulli free boundary problem. Thank you, Dennis.
So thank you very much for Daniela, and thank you for having me here. It's a pleasure to tell you about this project. Um, let me also say that I recognize many experts on this topic in the audience. So some of the talk is going to be pretty elementary. So if you find it boring, then I apologize. But I will try to get to some things I have been doing recently with Georg Weiss, which hopefully will be still interesting. So this whole project that I talk about it will be is joined with Georg. But okay, let me start with some background. So this is the Bernoulli free boundary problem for in the form that I want to talk about today. So I have some domain uh, in Rn. The domain doesn't matter. I put the domain here to make some statements of theorems later on precise, but most of what I'm interested in is in some sense local. And I am going to try solving this Bernoulli free boundary problem where I have a function which is non-negative and it's either positive and harmonic or it's zero. And along the boundary of where it's zero, I also put this overdetermined condition that its gradient is one. And so this makes it overdetermined. I can't generally, given a boundary here, solve both that u equals zero and that the gradient is one on the boundaries. There's too many boundary conditions. I think of this as a free boundary problem. Uh, I let my boundary of the domain also be a boundary of the positivity set here also be free. So I have two unknowns in some sense and two boundary conditions. Um, so this is the boundary. This is the Bernoulli free boundary problem as far as I'm concerned. The kinds of solutions I talk about, I will talk a lot about what kinds of solutions I care about, but at the moment, let's just talk about smooth solutions, like classical solutions. Classical solutions means something like the uh, boundary of the positivity set here is a smooth hypersurface, and u is positive on one side of it, and from that side, the gradient equals one. That would be like a classical solution. Um, And let me remark, there are many ways you can rewrite this. One of which is that uh, this is the normal derivative, right? So the tangential derivative is zero along the level set of u. So really, this is just a condition on the normal derivative. Okay. Um, so there are various motivations for studying this problem. The reason I call it the Bernoulli problem is that it appears as well in the context of stationary Euler equation. So if you have like a fluid with a free interface, so like water and then adjacent to some air, and the law governing the motion of fluid, well, there are kind of two boundary conditions there. One of which is that the the boundary and matches correctly with the direction of motion of the fluid. But there's another one which is that on the pressure, that the pressure is constant along the surface of the fluid. And so if you look at stationary solutions to this rather than dynamical solutions, um, and you change variables appropriately, you get to this problem in some sense. I mean, you need to make a lot of assumptions about your fluid to get actually exactly this. Uh, they would have to be like irrotational, so you actually have this equal to zero, and so on. So uh, this is very simplified from what fluid theorists would actually be interested in, but this is kind of the most straightforward model that you can come up with. There are other applications like from parabolic equations like flame propagation various optimization problems. I study shape optimization problems a lot that kind of reduce to problems like this. So there are many reasons you might want to study problems like this, let's say. Maybe not this exact problem. Maybe you're interested in some kind of perturbations of this. But this is the simplest archetype for this kind of problem. And so that's why I focus on this one. Okay. And we're going to ask typical PDE questions, like are there solutions? What do they look like? Um, and so on. So let me start by giving you a lot of examples of solutions. I will give you a lot of examples. Um, First, there's kind of a trivial solution where U is strictly positive everywhere. If U is strictly positive, then it solves this trivially if it's harmonic. You don't have to check these conditions because U is strictly positive. So there's nowhere you need to check them. And if I prescribe boundary conditions in the boundary of a domain, then I can always solve, if I prescribe non-negative boundary conditions, I will always get a positive harmonic function out of it. I can always find solutions which are trivial like this. You also have U equals 0, of course, this solves it. But in 1D, there are also some non-trivial solutions, some solutions other than the harmonic function. So here I have some pictures of them. I apologize for the pictures. The pictures are not great. But so what's going on here? So this is the 1D solutions. We've classified the 1D solutions in this picture. So there's these have to be piecewise linear because either it's 0 or it's harmonic. So here, this is the place where it's harmonic. This is 1D, so it's just U double prime equals 0. It has to come in with a slope of 1. So here U prime had to come in with a slope of 1 here. And then here was 0 to one side. So this is a classical solution here. And there's another classical solution like this, right? And there are some more where you have two free boundary points. You have two free boundary points. So these are all of the classical solutions essentially up to, moving them around. So, one thing I want to observe about these 1D solutions is already like very relevant for the rest of the talk is that, well, you can take limits of classical solutions, let's say like some bounded classical solutions. You take a limit, one limit. So most of the time that doesn't is completely uninteresting. But there's one limit you can take where you take this one and you move these two, points closer to each other. And in the limit, you see this configuration here, which has one free boundary point, but U is positive on both sides of it. So this is not a classical solution as per my definition of classical solution. You could, of course, talk about solutions like this where you're kind of positive to each side, but the point is that so like you can get this as a limit of these configurations. Okay. So these are these 1D solutions that I mentioned. Okay, there's also radial solutions. We can, in higher dimensions, we can look at radial solutions. And well, what is going to be harmonic, right? So here U is harmonic. And there's going to be some region where U is 0. And whereas harmonic, it's still radial, so it's just a multiple of the fundamental solution. And you can see that there's a unique radial solution once you specify the radius of this 0 set. And okay, you can compute how these behave. And the only observation that's going to be important here is that, well, as you choose a smaller 0 set here, so as I kind of decrease the radius of this ball, this solution goes to 0 locally uniformly. So you can check that by just computing which multiple of the fundamental solution this is. And so you compute, and so the solution goes to 0. So in the limit, you see the 0 solution, which is fine. It's a solution. But here, notice that the free boundary of the so here, like the free boundary converges to a point, but the positivity set of U. So you see here, U is positive, right? But in the limit, the U was just identically 0. So the limit of the positivity set is not the positivity set of the limit. Okay. Okay, you might ask, what are there some other solutions we can produce? So another interesting entire solution. This is uh, there's a family of entire solutions in 2D which are periodic. So uh, these guys and Troze uh, construct and then classify essentially all periodic solutions in 2D, periodic with respect to one direction. And there's a one parameter family of periodic solutions up to the invariances, and the parameter corresponds to sort of the size of these ovals that you're seeing here. There's one with smaller ovals, there's one with bigger ovals. So the way they look like is that top down, the zero set would look like around every, so let's say I'm one periodic, then around every integer multiple here, there's a convex domain, a smooth convex domain. And there's a function, so that's where u is zero. So here u is zero, and u is positive everywhere else. And as you sort of zoom out, this is pictured on here is sort of you take your harmonic function, you zoom out, and as you zoom out, it looks more and more like a multiple of that absolute value solution we had before, like this one, right? So this absolute value x, terrible job here. Right, so we had this solution in 1D. So here it looks like a multiple of the solution, but you can compute, and it's not so here you're going to get some multiple here of, let's say, x2, where x2 is the direction orthogonal to the direction of periodicity. But this alpha is less than 1. Alpha is some number strictly less than 1. So uh, yeah, so here you see, so like so there's one parameter family parameterized by some alpha, which is related to the size of this convex set. And there's a solution corresponding to it, and at infinity, it looks like alpha times this mod x2. So here, if you just take this blow-down limit, if you take a limit as I zoom out, they converge to this. They just converge to this. So I have and these are classical solutions. So I see this thing, which is not really a solution. Well, it's not a classical solution, right? And if I want to accept this as a solution, it's a little bit surprising that I should be doing that because, well, it doesn't satisfy my free boundary condition in any meaningful way, right? Its slope is not 1 as a limit of classical solutions. So uh, this is just a phenomenon that occurs in 2 or more dimensions.
Dennis, I
Yeah.
just have a little question. So the convex sets as alpha tends to 0, they become smaller and smaller, and the period is still 1, right? So what I'm
Yes,
saying
period
as alpha
1.
tends
That's
to
right.
0,
That's right. Yeah.
if I keep period 1,
Yes.
the convex sets get smaller and smaller. And as alpha tends to 1, your convex sets sort of become very long ellipsoids. Is this
That's
correct?
right. They're like thin and yeah,
They're thinner, and there is this
something like this. Yeah, and they also get thinner,
hairpin
right?
solution, right? That if you
Yeah,
blow up around the tip,
that's
you
right. That's
have
right.
the infinite
Yeah.
convex sets on one side in the air, right?
Yeah, that's right. That's right.
Okay, thanks.
So in fact, I think you can relate, you can compute here that alpha has to correspond to the perimeter here by just integrating by parts. And yeah, you can compute that they look kind of like this. They have this thing in Troze is very precise. Like they have formulas for this almost. And it's okay. So how do we actually? So the goal of this talk is to come up with some kind of notion of solution that I like, which can describe the phenomena we observe here. So if you read the literature on this, I would say the most common approach to this problem is via like this energy method using the Alcafarelli functional. So let me talk a little bit about that. So you can write down this energy, right? So fix your domain, and you can write down this energy. Before I was talking about entire solutions, but let's sort of fix a domain to do this locally. And this is energy. You can compute the first variation of it. So this is the energy. I have a digital energy plus the volume of the positivity set. And okay, so if I look at the first variation of this energy, you can compute it, and you just get this Bernoulli problem. So at least formally, if you can, if you have a classical critical point over this energy, then you will have a classical solution to Bernoulli. This is just a computation. The computation, I mean, this is like due to Hadamard for not for this, but for the first eigenvalue of the whole plot. It's very classic, this Hadamard variational formula. Alcafarelli did this for exactly the problem I'm describing here. And they justify rigorously, for example, that if you have a minimizer of this, then it satisfies the Bernoulli problem, at least in some appropriate sense. Okay, and the great thing about this is that you can minimize the energy, right? You can just take this energy and you can minimize it using direct method. You take a limit of a minimizing sequence, you show it converges, this thing is lower semi-continuous, it just works. And so given any boundary conditions, you get a minimizer. And minimizers are stable undertaking limits. Limits of minimizers are minimizers. This is just like a calculus variations fact in general. I mean, they're stable under limits. They also have a beautiful regularity theory that we'll touch on. I don't want minimizing solutions. I don't want, so today my goal is to talk about solutions other than just minimizing solutions, because minimizing solutions are restrictive. So being minimizing is not like purely a local property of the solution. It has to do with the domain in which I'm a minimizer, and it rules out a lot of solutions that I actually care about. So I'm not satisfied with just working with minimizers. So what do I want to do if I don't want to work with minimizers? I want solutions which, okay, they solve the problem somehow. They include all of the classical solutions I've described. This is actually a problem with the minimizers. Not all of the solutions that we've seen are minimizing. We'll talk about this in a moment. And they include limits of classical solutions as well. So there's kind of a dual question to what kind of notion of solution I should use. It's what do these limits actually look like, right? So this is so to describe what I actually want to do here and what I care about, let me introduce one piece of vocabulary. So I will call a regular free boundary point one where the Lebesgue density of the positivity set is less than 1, between 0 and 1. It cannot be 0. You can prove it cannot be 0. So strictly between 0 and 1. So these are like the points where you have a decent amount of the 0 set nearby. For all of the notions of solution that we'll describe, this is going to be smooth except like on a high codimension set. All of the notions of solution that I describe will have essentially the same behavior at regular points. I will use singular to describe any other free boundary points. So those with Lebesgue density 1 for the positivity set, Lebesgue density 0 for the 0 set. So the classical solutions weren't supposed to have those, but as we saw, when you take limits, you do get things like the absolute value, right? And this absolute value solution does have a singular point. This is a singular point because it has 0 density for the 0 set. And the behavior here is more, I mean, it's unclear what the behavior should be. So this is kind of the focus of what we're studying. So why do I care about doing this? Why do I care about limits of classical solutions? One is that for some of the applications I mentioned, there's no reason to look at minimizers, right? If I'm studying water waves, then they're not minimizing anything. They're just stationary solutions of Euler equation. If I'm studying parabolic equations, they're not minimizing anything. They're just stationary. I mean, if I'm getting this as stationary limits of parabolic equations, then you know, there's no minimality there. There are shape optimization problems that are like of min-max type, and those will give you things which are not minimizing. So the applications, there are I think reasonable applications of this problem that focus on solutions that are not necessarily minimizing. Also, if you want to construct solutions by any method other than just directly minimizing the Dirichlet energy plus volume that I showed, the all-Caffarelli functional, you're probably taking limits of solutions, right? You're probably taking limits of solutions. And so being stable under limits is very important for that. So as an example of that, one thing you can do here is you can take any semi-linear equation where like the F is bounded. So like I want to be maybe non-negative and bounded here. And so I want to be bounded, and I take one which is compactly supported. So if the F is compactly supported, you can rescale like this. And sort of formally as distributions, when you rescale like this, the F converges to a delta function. And so up to slightly changing the variables here, you will converge to a solution of Bernoulli. What kind of solution is unclear, but at least formally, you expect to get solutions of Bernoulli problem when you do this. So, and this is in principle a very effective way of constructing them because, well, this is a semi-linear equation. This is better behaved. There's no like free boundary. It's just you're solving a very well studied PDE. But to actually do this, you need to study. You need some kind of estimates for this limit, and you need to study what happens to what becomes the free boundary in the limit. So this is also one of the things that I'm interested in doing here. Okay, so let's talk about the possible notions of solution quickly. So minimizers, I already mentioned minimizers, right? A minimizer just minimizes the energy with respect to let's say some compactly supported perturbations. Minimality is not like a local property; it's a global property, and so let's check which of our previous solutions are minimizing in which domains. So these in 1D, the regular solution, the xn plus the type solutions are minimizers everywhere, but the absolute value of x is just not minimizing. This is not minimizing. This you know, you can just beat it with a competitor. And if I look at something which converges to the absolute value of x, right, then this will be a minimizer until they get too close to each other, and then at some point it stops being a minimizer. The minimizer is instead the harmonic function, the function with no free boundary. So in other words, if I'm looking at this thing, then whether or not I'm minimizing depends on how close these 2 points are to each other. If they're too close, then instead the minimizer will be this linear function because that's, you know, so that just has smaller energy. Okay, so minimizers only have regular points. They have no singular points, and they are stable under limits, as I mentioned. So this is a great notion of solution. It's stable under limits. It has everything I want, except it's restrictive and it does not include some of the examples that I want to work with. Okay. So if I don't want to do minimizers, what else is available? One thing you can do is look for solutions which are stationary for the energy, right? So I look at the same energy. I don't ask for minimizers anymore. I look at solutions where if I perturb the function by some compact perturbation here of order t, this is of size t, then the first variation is 0. There are two ways you can do this, kind of like in in other variational problems, like in harmonic maps or whatever, right? You can either perturb the target or you can perturb the domain. So perturbing the target here means I'm adding so I'm perturbing the harmonic function, the H10 function itself. So I add a H10 perturbation of my U. I make sure it stays positive, and so I'm varying what my function is doing in the target space. So I'll call this target variation solution. In 1D, what this means is that at every free boundary point, it has to look like x plus or x minus. That's all it means. So in particular, this is not a target variation solution like this. But the classical solutions are all target variation solutions. So that tells us immediately that these solutions are not closed under taking limits. So I have again these sorry, I'm having trouble drawing this. So the solutions which we're converging to the absolute value solution. Right, those are target variation solutions, but they converge to something which is not. So this is a problem with this notion of solution. It's just inherently not stable under limits. It has no singular points, and so it has a good regularity theory. And this, for example, all Caffarelli studied essentially regularity theory for this kind of solution in their original work. So this is very natural, but it's not stable under limits. So I don't like it. Okay, you can instead do inner variations. Inner variations means you compose with a diffeomorphism of the underlying domain, and that should not change my the energy to first order. So so I have a vector field. I take a flow of the vector field, and I push the U forward by the flow, and I look at how much that changes the energy, and that should change the energy to a higher order than first. Okay, so this is more restrictive than looking at outer variation solutions. But this is actually how you derive the free boundary condition from the minimality of the all carefully functional, for example. So this is very typical. People do this often, but they don't necessarily look at solutions which are purely defined by this inner variation. So I'll call these domain variation solutions, and these are actually the ones I want to focus on today. In 1D, if you think about what this means, you figure it out. So what this means is, okay, at any free boundary point, you have to look either like x plus, x minus, or like a multiple of absolute value of x. So any multiple. You don't have any control over the multiple from this definition. But it has to be the same multiple on each side, right? So alpha times x plus alpha times x minus. So this allows these singular free boundary points, but at those points it forces some kind of matching condition from the two sides. That's what this appears to be saying. So this includes limits of all the previous examples that we looked at, right? We looked at the radial functions going to 0. Those are all domain variation solutions. The Tresay solutions are classical solutions. They converge to a domain variation solution because it will have an alpha less than 1 here. but it's of this form. So actually, this includes all of the solutions we've seen so far, unlike the other types. So it's reasonable to ask here, okay, are these actually stable under limits? And that's one of the things I will try to prove. Well, that's one thing we can prove. That will be one of our theorems. Before we get to those, let me also mention viscosity solutions. So viscosity solutions are a completely different kind of solution, which have to do with maximum principle. So this problem has some kind of maximum principle, or it has like a comparison property that you can use to define viscosity solutions. Viscosity solutions are okay. So if you figure I don't want to actually state what a viscosity solution is, but the things to know about viscosity solutions is they are stable under limits, just kind of for free. This is just automatic for viscosity solutions. So that's an amazing property of them. But if you look at what they say in 1D, okay, so at a regular free boundary point, one with lots of zero set, they tell you you have exactly the right thing. But at a singular free boundary point, all they're going to tell you is that you're like x plus, okay, so you're a multiple of x plus from one side, you're another multiple x minus from the other side. The two multiples don't need to match. So it's not giving you this matching condition that the domain variation solution was giving you. Instead, it's telling you that both slopes have to be less than or equal to 1. What happens is essentially there's a viscosity subsolution property and a viscosity supersolution property that's telling you that the slope is less than or equal to 1 or is greater than or equal to 1. And at a singular point, you can only test one of those. So like the viscosity subsolution property is giving you what I wrote here, and the viscosity supersolution property is not giving you anything because there's just not a point at which you can touch by the appropriate objects. So viscosity solutions have this kind of issue at singular points where they kind of, well, they tell you that your slope is bounded from the two sides, but they don't tell you anything else. So in particular, there's even less of a meaningful free boundary condition than for the domain variation solutions. And as far as I'm aware, you can have a very terrible behavior if you just assume this. Like this is too weak to say very much about how the singular set can look like, which is something I will tell you about for the domain variation solutions in a moment. So if I tell you you have a viscosity solution, you just can't say very much at all about the singular set. Okay. So if you buy into this stuff that I just told you, then variation solutions they seem like a good idea. They seem like a good bet. So are they actually stable under limits, right? That was like one of my main things I was looking for, stability under limits. So this is what I have to try to convince you of. You can write what it means to be domain variation solution, and you get this. So for any vector field, I can construct a flow and test against the flow. And when you do that and you compute, this is what you get. Maybe this looks, I don't know. So if this looks unfamiliar, then if you omit this term, this is what it means for a harmonic function to be stable, right. So this is like the domain variation minimality of a harmonic function. So that's a property of harmonic functions. This maybe not used all the time, but is just a classic property of harmonic functions. So this is the only thing that's different here. You have this characteristic function. So let's try to show that it's stable under limits, right? So I take a sequence of them, converging strongly in W12, right, in H1. So I don't really care about how strongly they're converging. It's not difficult to find compactness for these solutions in very strong spaces. They have good estimates. So that's not really the worry. And if you do this, then well, this term and this term pass to the limit just fine. So the only issues with this term. So if I'm trying to show that the limit is a domain variation solution just by taking this equation and passing to the limit, I want to show that this converges. So this is the characteristic function of the positivity set of U. This converges to the limit of, right, which should be the characteristic function of the positivity set of the limit. But we know this is false. We know this does not always happen because, for example, in that radial example, these were converging to 1 everywhere in space, but the positivity set of the limit was empty. So this was converging to 1 almost everywhere, but the limit had this be 0. So if you just stare at this equation, it's not clear how to pass it to the limit because this term does not pass to the limit. Okay, what you can't show is that there's some compactness for these functions as well. So they do converge to a function, which is like a BV function taking values in 0, 1. So it's a characteristic function of a set of finite perimeter. But that doesn't tell you that it's the characteristic function of the right set of finite perimeter, the one where corresponding to the positivity set of the limit. Okay, so the previous theorem that was kind of available for this, this is due to Georg from I guess 20 years ago, is that the limits of domain variation solutions are some kind of generalized domain variation solutions. Generalized meaning that, well, like this function here is decoupled from the positivity set of U. And they satisfy the following distributional formula. So if you can write the PDE for U as a distributional equation for the Laplacian, right? So the free boundary condition is supposed to be telling you at regular points that the Laplacian is like the n-1 dimensional Hausdorff measure restricted to the regular points. If I have a classical solution, this is just true. Like this much is all. This is exactly what the Laplacian, when I view it as a Borel measure, is for a classical solution. So Georg showed that, okay, for these variational solutions, you also have this at sort of regular singular points. So there's this sigma double star here are singular points where you locally have a tangent, and your function locally looks like absolute value of x. This is like the absolute value of x in some direction and with some multiplicity. And in that case, the contribution from that is also exactly what you expect. If you have smooth singular points, then this is what you expect to get. And then there's also this stuff, this stuff with sigma z, this part here, where lambda is some Borel measure, and this is like the rest of the singular points. So Georg could prove interesting things about this. He can prove that this is rectifiable, for example. But he could not prove anything about these things. So he could not prove that there's no estimate on the size of the set. It could maybe, have like positive Lebesgue measure. And there's no estimate on this Borel measure. So it's not really clear what this term here is doing, whether it should even be here, or what the deal is. Okay, so this was very difficult for him to prove because actually estimating this set without any knowledge of this one is challenging. And so it's remarkable he could do this, but at the same time, it was difficult to use. It's difficult to use because of this extra possibility of kind of these degenerate singular points. That's really what's going on here, is that you have like lots of singular points where U is like very flat here.
Sorry, Dennis. So
Mm-hmm.
in this theorem, there is no what is the Hausdorff dimension of sigma z?
There's no estimate on the Hausdorff dimension of sigma z.
So okay.
So yeah, so it's sort of unsatisfying in that sense, right? Like this could be very large. I mean, these are singular points, right? So it's not like every point is in sigma z. These are points where you have zero Lebesgue density for the zero set. So as long as you have some zero set, you have other kinds of points. But it's not clear what what the yeah. So there's no real information available about this.
And so far in your examples, you didn't give an
Yeah.
example of any of that, right? So
Right. So I mean, so it's possible to produce examples that do have sigma z, but much less than what this would suggest. For example, if I take any harmonic function, any sign-changing harmonic function, I take its absolute value. This is a domain variation solution according to my definition, because there's no zero set, so there's no. I mean, I'm not. This just isn't doing anything. Um, but but it satisfies the formula then. So it is a domain variation solution, and it has points where so the point, if I have a point where the harmonic function vanishes second or higher order, that'll be a point in sigma z.
but
Because
those
locally you're
wouldn't
not.
have, they don't have any mass or anything like that.
Yeah, that's right. So there's a codimension 2 set of points, right? Because it's so you might expect sigma z to be like codimension 2 heuristically. But that wasn't. It's not possible to prove.
But
We still don't know how to prove that here. So um,
okay, but even like that, even if it's codimension 2, it's still the measure of
yeah,
Laplace.
the measure would then be zero. The measure would then be zero. The only way the measure can be positive is that if this has somehow dimension larger than codimension 1, so dimension larger than n-1, dimension larger than these things.
Uh-huh.
Okay. So we now have a better theorem. So here's what we can prove now, 20 years later. So let's say U is a limit of domain variation solutions. We prove first that U itself is domain variation solutions. So domain variation solutions are closed under limits. And either UK converge to identically zero. Here, to make this precise, so remember that omega here is connected. Otherwise, you do this in each component, connect. So either the limit was zero or the positivity set converged to the positivity set and the free boundary converged to the free boundary. So those radial functions that were converging to zero were like a counterexample of this, but that's the only counterexample. That's the only thing can go wrong is the U K's just converge to zero. We now have the formula for the Laplacian, which is the previous formula without those terms. So the measure there is zero. And the full singular set is has locally finite n-1 dimensional Hausdorff measure and is rectifiable. So the sigma z, so this theorem is not saying that sigma z is codimension 2. I don't know how to prove that, but it is saying that it's at worst codimension 1 and it's rectifiable. So here it looks like these other singular points that okay, so this is I think much more usable than the previous theorem because yeah, we don't have this extra error term. It's what you expect. This is what you would expect. Okay, let me say a few words about what goes into the proof here. So we we look at our domain variation solution, right? And the first thing you can observe is that the domain variation property is enough to tell you that this monotonicity formula holds. So this is like the classic monotonicity formula for the Bernoulli problem. This is due to I mean, so I guess this is due to Georg as well from a few years earlier than the previous paper I mentioned. So this is monotone. This is a non-decreasing function. And if you take the limit at zero, you read off the Lebesgue density of the positivity set. So the Lebesgue density only has some possible values because you can classify, well, or you can at least say something about the possible blow-up limits of the U here. So okay, so the only possible values are, so either you have zero. Zero means that you were like blowing, you were doing this at a point in the interior of the zero set essentially, or you have a density between 1/2 and 1. And I guess I should, right. So this is poorly phrased. This is the limit of this. But so the point is the density can only be between 1/2 and 1. I should have written it, but this is 1/2 and 1 here. Okay. So the singular points are those where it equals. So I can read off whether a point is a singular point by looking at the limit of this function. So what, right? This doesn't actually help you to say anything about the singular points, because at the sigma z singular points, if you blow up using this formula, you get 0. That's what characterizes those points essentially. So what we do instead is, okay, we write down this frequency. This frequency is, so this is like Almgren frequency plus something specific to this problem. This is like the characteristic function of the positivity set. This quantity is increasing at points at any singular point. In fact, at any point where the monotonicity formula was larger than its value at a singular point. So at any singular point, I have another monotonicity formula. And this one, if you blow up according to this formula, you never see 0. You are normalized in a way that you will not see 0. And it's supposed to read off the order of vanishing of U at X, right? That's sort of the idea behind these frequency formulas, is that ignore this part. So then this is reading off the homogeneity of U at X asymptotically. You might expect this to be 1, but as I mentioned for that harmonic function example, right, it can also be larger. Okay, this is so, but those harmonic functions have singular sets which are codimension 2, right? Where the points with higher frequency than 1 are codimension 2. You can ask, is that still true here? So what you're supposed to do is you're supposed to do these Almgren blowups sort of normalized by this frequency. And here you can do this. You can construct these. You can take a limit of these. But what's not clear is that PDE passes to the limit, right? Because the U, it was not just harmonic, right? It was harmonic, but it was also satisfying my free boundary condition at some points. So if I try to pass that to the limit, here I'm dividing by a really small number. So at the points where I'm on the free boundary, like it's not clear how, like what that passes the limit to. Okay, so Georg knew how to do this. Well, he knew that this formula was monotone, but he was stuck on this point where it's not clear what to say about the blow-up limits of this. So in the years between the two results, Neighbor Valtorta came up with kind of a more quantitative approach to studying the singular set than just doing these blow-ups. And essentially what they're saying is, okay, it's enough to do these blow-ups at points where the U is approximately codimension 1. Because if the U is not codimension 1 anywhere, then it's like it has to be codimension 2 for purely like, so the set of points where like the U does not look codimension 1 is like codimension 2 for purely GMT reasons. Like if you have a very large sigma z, the bad singular set, then you should be able to find a bunch of points in there where they're kind of in general position with respect to n minus 1. So if I blow up at, so if I kind of look at points like that, then there my harmonic function, it looks almost codimension 1. So as long as you can say something about doing Almgren blowups at points where you have extra information, where the U is like approximately codimension 1, you can still prove estimates on the size of the singular set. That's like a very rough idea of what we're gaining from the Neighbor-Valtorta method here. And for us, this is ideal because at a point, so if I do a blow up and I know that the limit is codimension 1, I can actually classify them and I can pass the PDE to the limit. Like I can upgrade the convergence of this to the limit essentially, because like the limit is so restricted. And so we can do that. We can make this work essentially. So from this, with some effort, you get that the singular set is rectifiable and has finite n minus 1 dimensional measure, including the sigma z part. This implies that, so this implies a convergence theorem I mentioned. So if I have a sequence of the variational solutions converging to a U, what I just described also works for the limit. It's just, so the limit also has this. So if there's a region where the limit of the positivity set is larger than the positivity set of the limit, then you look for points in the boundary of this region, which are like regular points, essentially. They're not regular points, but they're regular singular points. And because of the rectifiability and size estimate here, you're guaranteed to have some points like this. And locally looking like this at a point where U is 0 on one side of it is a contradiction. It's not, these are not compatible. If U is locally like this, but U equals 0 on the boundary of like such a point, and this is a point of rectifiability, then this is just not possible. And okay, so this implies the convergence theorem I mentioned. With some GMT arguments, you can also get this formula for the Laplacian, and with some PDE estimates, you can prove that the free boundary converges to the free boundary as I described. So this regularity result is enough to prove everything else I mentioned. Okay, let me just make a couple of remarks in conclusion here. So we feel that this makes working with non-minimizing solutions to Bernoulli more accessible. So constructing solutions via limiting arguments or some kind of min-max or some constrained optimization, looking at sort of studying global solutions, like entire solutions, and trying to classify them, or taking limits of entire solutions. This is all kind of more doable in this framework. And there's a lot more that should be true about the structure of the singular set than we prove, right? Maybe you should be able to prove that sigma z has 0 and -1 dimensional measure, for example, but we're not able to do that at the moment. This is, I think, reasonable and interesting. And you can try generalizing this to other equations, right? So I gave you this for the simplest possible Bernoulli problem. You can ask, is this true for other Bernoulli problems, and so on. And, this is all reasonable, and hopefully, okay, this is just the beginning of working with stationary solutions of this type. Okay, so thank you very much.
Thank you very much, Dennis, for a beautiful talk. And I believe someone raised their hand, so perhaps you can address their question.
Okay, yeah, just
it was me. It was just a mouse slip. It was not.
okay.
I don't have any
okay.
questions, but the talk was
Okay,
great.
okay.
Thank you.
Yeah.
Okay, but maybe there are other questions at this point.
Maybe just a quick question. So you mentioned that, in the limit, you only converge to either zero or the other solution. Can you, characterize which cases that you converge to zero, which cases you are not?
Well, I don't know exactly when you converge to zero. I mean, so of course, like given the family of solutions, so you will converge zero. I mean, so like if you, this does imply something about how the free boundary has to look like in principle, I guess. But you can have so since you're not looking at entire solutions, there's not like a lot of rigidity here. I imagine you can have lots of examples where you converge to zero, but I don't have a great answer to that. I don't have. I think that's actually. I mean, yeah, that's pretty reasonable to ask. Like, what are the possible ways you can converge to zero? Like, what does your free boundary have to look like if you're converging to zero? But I haven't thought about it, so I don't have anything intelligent to tell you about it. Yeah.
Thank you.
I mean, I think you expect that if you're converting to zero, when you converge to zero, your Laplacian here converges in the sense of distributions to the to zero. So your free boundary, like this regular part of the free boundary has to go to zero then, and here though it's not completely clear like what has to happen, because it might just be that this is still large and you're kind of more spread out. But if you have a classical solution converging to zero, then your free boundary has to go to zero. At least it's the length of the n-1 dimensional measure of the free boundary has to go to zero. And that's like if and only if, I guess, because just but as far as the actual geometry of how that can actually occur, I don't really know. We should have more examples, but I don't know that we do.
Thank you.
Other questions, comments?
I have a question. So, okay, I guess I have a couple questions, but very nice talk, first of all. So it seems like, you could combine it with viscosity solutions, right? You could have something that's
Yeah.
both.
I think it's the right thing to do.
Yeah, because I like alpha. There's no limitation on alpha, right? Like if it was a viscosity super solution, alpha would need to be smaller than 1, but you have no.
Yeah. So I think it's most reasonable to look at like viscosities plus variational solutions, something like this. Yeah. Viscosity solutions have a great estimate, right? They tell you that your solution is its gradient is bounded by 1 along the free boundary, and so like by Bernstein, it's bounded globally. So it gives you compactness, and this gives you some characterization of the free boundary. So I think that's a great class of solutions to look at, as like viscosity solution plus domain variation solution.
I have another question. Sorry, I have like 3.
So
what about like viscosity minimal super solutions or maximal subsolutions? I guess those don't necessarily behave well under limits, but
yeah. So like the if you look at the most stable, so like there are these viscosity solutions which are right. So if you choose the most stable ones, they're almost minimizing somehow. I don't know if it's I'm not I don't know the theory completely, but so I don't know if you can show that they're actually minimizing for this particular equation, but they're stable, right? They're stable. So They will not have singular points. But they have, it's also like not exactly a local notion of solution. I think it's very it's similar to minimizer theory at that point. So if you're looking at like the ones that Caffarelli constructs, for example, using the Harnack inequality approach, like the Perron solutions, I think that's closer to minimizer theory than to this. In particular, they have the non-degeneracy and the volume bound, like the volume bound on the zero set at every point.
I have one more question. So, so I don't know exactly how to pose this, but it seems to me that if you were to try to make some notion of genericity by like, doing some moving up some boundary data or something like that, that it should be kind of like in the kind of space and time. You should have even less points that have this alpha of x hn-1 form, because don't you need to have like a significant portion of the free boundary kind of touching it? That seems pretty unlikely to happen. I mean, I'm just thinking of like some kind of, if you think of like two bubbles of positivity set, when they hit and merge, they're not going to hit even along a n-1 dimensional line. Is there some possibility that there's
yeah, I mean, I think that seems reasonable. They're not, I mean, so the only like topological reasons are like forced ways to get them to have these points, as far as I'm aware, or would give you like a codimension 2 set of them, right? Like there's no argument that says that you should have more than codimension 2 of them. In some like, there's no mechanism for forcing more than that, as far as I'm aware. But I don't know how to prove that. I don't know how to prove that. So I think that's reasonable. But yeah, I'm not sure. I'm not sure how to prove it. I think it's a good question.
Thanks.
So if there are no other questions, we can thank Dennis again for a very nice talk. And
thank you
everybody for attending.